Okay, everyone, welcome to Physical Chemistry. In today's lecture, we will be talking about molecular structure, valence bond theory, and beyond. Within valence bond theories, one of the initial things that we should know about is the Born-Oppenheimer Approximation. At a valence bond theory, we've got four major topics that we're going to focus on, but they do revolve around the Born-Oppenheimer Approximation first and foremost. The sigma bond, or pi bond, spin pairing and hybridization are some of the main concepts. And let's recall that all of this information is going to be centered on solutions of the Schrodinger equation. We should be extremely familiar with this at this stage. Now, the Born-Oppenheimer approximation assumes a stationary nuclei and also assumes that the electrons are mobile. And when this is the case, then we make our equations for the Schrodinger equation and then get our necessary solutions. Now, for a diatomic molecule, we should go ahead and begin with the simplest diatomic molecule we possibly can, which is H2. And for the diatomic molecule, we should have a molecular potential energy curve. And this is going to describe the energy landscape of H2. And it's going to have some very critical concepts that are embedded inside of our molecular potential energy curve. Now, of course, like many of these, we've got energy on the y-axis, and now we've got internuclear distance on the x. And you've seen other diagrams that look similar to this. And what we're looking at here is the overall destabilizing and stabilizing force as two atoms are brought close together. And what you'll notice is that we've got this area of lowest energy. This happens at our equilibrium bond distance. And we also have the depth of the well, which we're going to understand as DO. And DO is our dissociation bond energy. And when we look at this diagram, you'll notice a couple of different things. One is that we go from a stabilizing to destabilizing force. And so what you can understand is as the nuclei get too close to one another, then the energy comes greatly up because the nuclei are becoming too close to one another and therefore are actually repulsive. But at the proper distance, we end up getting the greatest stability between our overlap of our wave functions described by H psi equals E psi and all of the interactions that should happen therein. Remember that these nuclei should be under a Coulombic potential because we have both a positive and negative charge from the electrons interacting with one another. For H2, let's now consider what happens when we've got them far apart for those particular wave functions. So, at a great distance, how do we understand those wave functions? Graphically, what we can go ahead and do is draw hydrogen A, hydrogen B, their wave functions at a distance where there is no overlap, and construct those wave functions for hydrogen A, hydrogen B for each one of those 1s orbitals. And for those wave functions, both 1 and 2 should be described by chi h1s sub A at a distance r1 and chi h1s1b at a distance r2. Now what you're going to understand is that chi denotes the atomic orbital, not the molecular orbital, and this will be a good distinction. Now the equation that we just saw can also be written as psi12 equals A1 B2 for our hydrogen and electrons respectively, electron number 1, electron number 2, and hydrogen A and hydrogen B. Because, and this is an important concept, because there is an equal probability of electron number 1 and number 2 being on hydrogen A and B. They are in a superposition, and the ability to discern whether or not they are on a particular hydrogen is not particularly possible. So to denote these two possibilities, we're going to say psi12 is equal to A1 B2 plus or minus A2 and B1. Now that positive sign is going to indicate the lower energy state, as we are going to see for a constructive interference. Therefore, we can write our wave functions for 1 and 2 as A1 B2 plus A2 B1, and graphically what we need to do is to draw what this looks like as we begin to bring the nuclei and their wave functions together. Alright, graphically, let's go ahead and depict this once again. We've got hydrogen A, we've got hydrogen B, but now they're in close proximity to one another. And we're going to draw these wave functions, but these wave functions now are going to have some special features, which we're going to see right here. And one of the main things that I want you to get a look at, and we'll go ahead and we'll change the color that we should have for this overlap, is now we're going to have this special area in between where we have a higher amount of electron density in that inner region. And what we have to think of is, what does that represent? And what we need to understand is that that wave function overlap is an integral, because once again we're asking, well, what's the probability density? And in another concept that we need to reinforce is that this is constructive interference of our wave functions. Constructive interference, because we have a particle wave, is a bonding orbital. And in the same vein, just like we can have the constructive interference of waves in the ocean or in sound, we can also have destructive interference of our wave functions and is a anti-bonding orbital. And you may have seen this earlier. This would be something similar to a sigma star or a pi star orbital. This constructive interference is the sigma bond. The sigma bond is a cylindrical, symmetric overlap in the internuclear axis. And if we wish to depict this, well, we've got HA, we've got HB. The internuclear distance is that direct axis that is right between our nuclei. And if we were to draw this cylinder, it would look something like that. If we wish to also depict those 1s orbitals, which should be right there, that overlap is in this region, we can go ahead and then depict that increase in electron density being in between both the wave function for 1SA and our wave function for 1SB. We are going to understand in a moment that we can describe this interchange of electrons and the sigma bonds by exponential functions. And I'll leave it with that in 1 second. Okay, now let's go ahead and describe that equation 10A.2, which is our 1, 2, A1, B2 plus A2, B1. Now if we were to expand this description, psi 1, psi 2, let's go ahead and spatially depict it as 1 over pi A naught cubed taking the square root e to the minus R1A over A naught times 1 over pi A naught cubed taken to the square root e to the minus R B2 by A naught plus those exchange of electrons which we discussed previously, 1 over pi A naught cubed taken to the square root e to the minus R A2 divided by A naught times 1 over pi A naught cubed taken to the square root e to the minus R B1 over A naught. And each one of these is describing, well, this is A1, this is B2, this guy is A2, and over here on the right hand side is B1. It's as simple and as elegant as that. And if we were to go ahead and simplify it, allow that mathematics to work itself out, we've got 1 over A naught cubed e to the minus RA1 plus RB2 divided by A naught plus e to the minus, what do we have? RA2 plus RB1 divided by A naught, and all has been taken care of. And you'll notice that, well, that's an exponentially decaying function going to the left, going to the right, from dead center where we would have our nuclei, and so this is our position R, and that would be where we should find our wave function. Thank you very much for your time, and answer the quiz questions later. Thank you so much.